Hello everyone. I'm going to read from my new book called Intense Design, and I'm going to read chapter 13, Applications. And I'll read it right from the book. I hope you're doing something interesting while you listen along, and thanks for joining me. So this is chapter 13 called Applications. Designers create order out of chaos, but design is not science. We need more than science and engineering in our quest to manipulate our environment. Engineering is based on theoretical, calculus-based presentations of concepts. Much time is spent in deriving equations and quantitative analyses. However, this approach doesn't always serve us well. How can you analyze something you haven't created? Even after concepts are agreed upon, the detailed design of the part requires many decisions that allow it to be lighter, stronger, cooler, or whatever the design goals stipulate. You have to put your best guess up for analysis. The multiple design decisions regarding an object's thickness, radius, roughness, etc. are based on having an intuitive feel for how solids, liquids, and gases behave. Typical design methodology calls for a sequence of events, which in their simplest form are 1. The clear definition of design requirements, 2. Development of concepts, and finally 3. Engineering the final design and manufacturing approach. However, many more ambiguous factors get introduced into the design process. Because design is done by humans, and typically for humans, a long list of factors are introduced into the development of designs, ranging from the sociological forces of group identity and organizational behavior to an organization's politics, individual egos, and ethics. Aesthetics asserts a subliminal force even on the most non-consumer design. Moreover, technical and business issues arise to provide design direction, such as ergonomics, performance, longevity, capital costs, and profitability. Regulatory forces such as safety standards often provide some baseline for starting a design, while corporate attitudes toward environmental sustainability and manufacturing preferences can suggest design approaches. Traditionally, design requires technical skills and experience to ensure that the product or system works in the way it is intended. Therefore, product design is often left to the engineers. However, intangible forces become integrated into the design and direct the final appearance of the design. The sometimes subliminal forces can be brought to light through an interdisciplinary study. Conviction versus doubt. Doubting is easy. Conviction takes work. This is true in most parts of your life, from religious faith to writing fiction. Doubt is nurtured by laziness and cynicism. Conviction about what you believe and your course of action takes guts, work, and humility. It may require going against the cultural currents and will cause grief, frustration, and a lot of work. What do you really believe? What do you think is the right approach? These are questions which are easy to ask but are difficult to answer. Running around being cynical and doubtful is not a virtuous state. Once you are convicted of something, you need to work it out in your own mind, so it is not a conviction that is contrary to evidence. How do I know if I have a good idea? Part of the inquiry can be mental, thinking through the design carefully. But part of validating your conviction is experimenting and testing. You have to build the thing you are designing and test it. It doesn't have to be a high-quality prototype. It just has to be something physical that you can work with. Many designers are reluctant to quickly move to a physical model. It is more peaceful to push a pencil or a mouse while you're sipping a cup of coffee and multitasking in other ways. Continuing. One of the problems with 3D printing or additive manufacturing is you can tend to use existing designs because it is easier to throw those digital files at your printer than to create a time-consuming CAD model. You may be very reluctant to change a design after you have spent hundreds of hours drawing a model. That is human nature. It makes sense to anyone that's used CAD. You spend a lot of time on a drawing, you don't want to change it. There are ways to avoid this problem of near plagiarism, meaning taking things from GrabCAD or some other online source and tweaking it and then using that, or overinvestment in CAD. Build your idea in cardboard, foam, clay, or wood, to name a few approaches. So just build something simple. Build your idea quickly. Test out dimensions, geometry, and mechanism. Does it fit in your hand? Does it look like something will easily break? Does your design have a chance of doing what you think it should? These issues will be very clear with a simple model. Check on control actions with hardwired motors or actuators. You can couple your simple prototypes with a microcontroller, programmable logic controller, PLC, or circuit board taken from a device similar to what you are working on. Don't requisition materials and issue purchase orders. Just scavenge stuff and use some of your coffee money and buy what you need. Cardboard, tape, hot glue, and string aren't expensive. So you can use drills and kids' toys and all kinds of things to make some of the things you need. You can be creative with how you test things. I've tied thin strings to the discharge hose of the shop vac and moved it around a model to see airflow behavior. You use discharge of the shop vac or something, tie some thin strings to it, and it's a little cheap wind tunnel. Anyway, this system makes a great, poor man's wind tunnel. I'm repeating myself here. I have tapped into a self-service car wash to provide high-pressure water for testing. So, if you need high-pressure, low-volume water, you go to the car wash and throw in some quarters, connect it to your design. Anyway, you can throw things off cliffs, hit them with hammers, immerse them in water, and perform all sorts of other home testing before you move forward with your design. I talk about several things here. I mean, there's some anecdotes in here. I guess I won't repeat them here. But I've made mistakes where I've tried to over-design things and ended up just wasting time. However, humility is required. Complex or high-speed devices will only operate reliably in a narrow band of optimized dimensions, tolerances, surface finishes, material specifications, etc. Complex machines require much more than hunches to make them work reliably. They involve solving a myriad of subtle issues that may not be identified in a lovingly guided working prototype. This is why it is helpful to tap into the expertise of others when possible, such as with gears, ball bearings, and lip seals, to name a few examples. In addition, complex machines need to be tested relentlessly. So, I talk about cardboard and hot glue gun and foam core and things like that, but when you're dealing with complex machinery, there's a lot of subtle interactions with dimensions and surface finishes and tolerances and so on. It's not trivial. Due to the cost and complexity of testing, you sometimes need to use a shotgun approach to solving problems that arise from these devices. That is, you make many changes between each test using a combination of 1. Determining what broke and why, perhaps through root failure analysis, and 2. Hunches about how you could improve the design based on testing. This is not elegant, but it is expedient and practical. The downside of testing is multiple changes is that you are uncertain what helped and didn't help the design. However, the motivation for shotgun approaches will be evident when you are involved with time pressure or very expensive tests. Speed bumps. Anything that slows down your design process is a speed bump. Speed bumps don't belong in conceptual design. However, speed bumps that slow down project development are valuable in certain disciplines such as engineering, manufacturing, and quality assurance. Some of these disciplines are addressed by having a good intuitive sense, especially for engineering. So you should see one of my other books for that. You should understand how materials behave and how heat and fluids move. When in the process of developing designs, you want to flatten speed bumps. Let's consider some of the speed bumps that can arise at the conceptual stage. 1. Slow decisions. 2. Overthinking. And 3. Changing design goals. So the first one, slow decisions. Deciding on a best approach is stressful. You want lots of data and proof. You want to see what your competitors are doing. You don't want to take risks. You want your boss's approval. The speed bumps presented by slow decision making can be ameliorated by 1. Recognizing there is no perfect design. 2. Authorizing a single decision maker who can decide quickly. And 3. Accepting mistakes as part of the process. The speed of design is slowed down in an environment where mistakes are not allowed or where you can't get a decision that lets you move forward. The process of design usually causes interpersonal friction. You contend with my way or the highway mentality as the harmonizer who takes a democratic approach to design. The harmonizer tries to make everyone happy. The autocratic route is efficient but could miss a design goal, and the harmonizing path makes everyone unhappy. Sometimes the customer doesn't even know what he or she wants. In the end, someone is not going to be happy with your design. You assemble a good team, accept displeasure with decisions, and use your charm and intellect to mend fences. Skunkworks was set up so that authoritative decisions could be made quickly. The challenge with that structure is that it can disenfranchise people, and any gaps in the armor of the decision maker gets pushed into the design. However, the results can also be stellar when an effective, efficient, and technically sophisticated person is in a position to make design decisions. Second topic, overthinking. Paralysis by analysis is a well-known aphorism. You are trying to do excellent work and create an excellent product. You want everything to be perfect. Unfortunately, design requires some intuition and guessing. This makes your stomach churn and anxiety swell. You want to solve a math equation, and all we get is a mass of partial information. While you can structure qualitative information into themes and process it statistically, you rarely get pointers saying, "This is the right design." Designers make something from nothing. That is our burden. Nothingness is scary. A blank sheet of paper. A good way to handle the overthinking part of the design is to rely on time-tested approaches that are commonly shared in design guides produced by manufacturers and professional associations. During my career, I have created several of these for a variety of products and systems. They are usually well thought out and completely grounded in real-world experiences. This may appear to close doors, but it lets you move forward quickly. After a product is fully created, you can go back and optimize things. Manufacturers and vendors want you to succeed with their product. The first time I worked with programmable logic controllers, I brought one home and read the manual while experimenting. I made a lamp turn on and off when commanded, and I felt increasingly confident in entrusting and programming the PLCs and other controllers with my designs. And that it went from turning lights on and off to leaving things in remote locations for years. So it's interesting. Ball bearing manufacturers are some of the best purveyors of design guides. They completely hold your hand and tell you exactly how to specify a bearing and design everything you need to support it. The same hand holding is available from many vendors and material providers. There is a role for careful engineering when you do explicit calculations to verify models. We take pride in our ability to do these things, so we are not enslaved to software. We then process parametric models through analysis software, such as finite element analysis and computational fluid dynamics, to gain additional insights into stress, heat transfer, flow patterns, etc. However, during initial design development, you are likely to get slowed by this type of minutia. Save it for a later day. And some of you are very familiar with this type of software. Some of you don't even know what I'm talking about, but there's a lot of software out there that can help you on the engineering side if you'd like that. But you don't want to become enslaved to it. And then finally, changing design goals. Changing design goals and mission creep are common, even though every bit of management advice you read will warn you against this. However, in the world of product design, goals are established with incomplete information. While a product's mechanistic goals might be clearly articulated at the start of the project, it often isn't clear at the onset whether the goals are achievable. This goal glare is especially true for advanced designs that explore new territories of science, technology, and human interactions. The time, talent, technology, and resource requirements are speculative. Moreover, the connection with non-mechanistic elements can be difficult to initially identify. So these are things that aren't, we'll say, technical, they're non-mechanistic. So aesthetics and brand and culture and these sort of things. In addition, through market research and product experimentation, you may see that your original goal is not practical. Safety concerns and product regulations can redirect what can be accomplished with a new design. Therefore, project schedules and Gantt charts need tweaking. So Gantt charts are for project scheduling. And goals are often more fluid than we'd like. These design goal changes can be minor or so large they derail a project. Nevertheless, they can easily be the biggest speed bump in the design process. So I hope you involve that discussion of speed bumps in the design process as you try to accelerate your designs. Thank you.